So now we know resonance and impedance, reactance. So impedance in series, you simply add. For resistors, you just are at an angle 0 or R plus J0. Capacitor is 1 over J omega C, an angle of negative 90. Inductor is Z. Impedance of an inductor is just J omega L plus 90 degrees. You can also remember this by the phrase Eli the Iceman. ELI is E-L-I. This means voltage leads the current for L for inductors. L is the letter in the middle. And then ICE, I-C-E, this is a current, which leads the E and the for the capacitors. But that has to do with phase shifting, and I might have that in another card. But Eli the Iceman, you can Google that. And that has to do with phases, which are definitely a factor because they have to do with how many degrees apart they are on your oscilloscope when you're testing and measuring such things. So for an RLC circuit, Z total equals R plus J XL minus XC, which we just reviewed thoroughly moments ago. For an RL circuit, just a resistor and an inductor together, the total impedance is R plus JXL, which is equal to R plus or J omega L if we don't care about the well, because right, it just happens to be that the J X of L is equal to J omega L, which is R plus 2 pi FL, because omega is just 2 pi F. I'll keep repeating that because it's just good to remember if you're going to deal with AC circuits. For an RC circuit, our total impedance is R plus JXC, which is equal to R plus 1 over J omega C, which is equal to R plus 1 over 2 pi FC when you go to apply the formula. 2 pi is always 6.28, F is your frequency, C is your capacitance in farads. Remember, capacitors usually come in, say, microfarads or nano or even picofarads. Convert it back up to farads whenever using this formula. Or simply remember that if you keep it at microfarads when solving it, your R is going to be in, say, could be in micro-ohms, or you could just do it with your powers of 10. I find it a lot easier to just convert up. I have a TI-89 graphic calculator, which makes entering powers of 10 very easy to calculate. And when you add complex numbers, use rectangular form. I already did a video for complex algebra. So the series AC impedance, here's parallel AC impedance. You deal with this very similar to as you would with parallel resistors, which is impedance. Let's say if we were to have just two elements in parallel, then we have our total impedance equals the product of the two elements divided by the sum of the same two elements, and that's our total impedance, just like if these were resistors. Be R1 times R2 over R1 plus R2. So the resistor, again, these are the same basic principles that we just reviewed. Or if you have three elements, it's the product of all three over the product of 1 and 2 plus the product of 2 and 3 plus the product of Z1 and Z3. If they're all different impedances in each case, and it builds out from there, there's probably more advanced formulas for that online. Or if they're all the same value, you simply take how many ohms of impedance there are divided by the number of elements. See, and that's exactly what I have down here. And complex algebra, because remember, you gotta account for your angles as well. So the series and parallel AC impedance. Admittance we touched on briefly. Here's more about admittance, which is the reciprocal of impedance. So y equals 1 over z. Remember, 1 over a number is its reciprocal. Y is what we use for admittance, z is the impedance, and z equals 1 over y. It is similar to our conductance, which is G equals 1 over, that's an R, resistance, reciprocal of impedance in Siemens. It's often used in parallel circuits. So resistors, Y sub R of a resistor is 1 over Z sub R. It's your angle, and there it is for your inductors. And there's also a property called the suspectance, that's a Greek letter beta, I think, or just a B sub L. 1 over X sub L in Siemens is the magnitude. So suspectance is the magnitude of your impedance, which is a suspectance think about it as how reactance is just the magnitude of the impedance. Its suspectance is the magnitude of the admittance. There's the capacitors. It's just simply the reciprocal angles are there. So the angle of admittance is the angle by which I current from the source leads the voltage of the source. So here we have the suspectance diagram of a capacitor, 90 degrees positive, and then we have for an inductor it's 90 degrees negative. Remember, that is just the opposite of our impedance diagram, which here these are side by side. So there you go. Alright, there's admittance, parallel RLC admittance. There's a diagram, simple parallel circuit, RLC. And it's very similar to parallel impedance. It's simply the reciprocal. So the total impedance is 1 over Y total. That's a T for total. XL and XC change in response to frequency. For a pure resistor, and this is just general for all of the cards that we've been going through for alternating current, a resistor has a flat response in response to frequency. The x-axis is what frequency. Let's say this is 10 hertz, 100 hertz, 1,000 hertz, megahertz. It's going to have the same level of, let's say, for example, current or voltage. It's going to have the same magnitude. For our reactance in response to frequency is going to go up straight because it's a plain old linear function. It's a multiplication function, 2 pi f. So this is just multiplication. We just multiply times the frequency, and as that goes up, the reactance of the coil is going to go up, and so is the impedance. For a capacitor, it is a reciprocal function. So because the capacitor is in the denominator, it's going to go like this and be, I think that's an exponential function. Correct me if I'm wrong, but that's the curve of a capacitor. And of course, at resonance, we want to find where the, so say if your capacitor is here at this frequency and your reactance is about here at the same frequency, if this value on the line equals this value on the same line, then guess what? XL equals XC if you overlap those graphs, and that's what a graph of resonance would look like.